So yeah, my presentation is about the micro and nano spacecraft contribution to the planetary defense mission. So I didn't talk about the overview for planetary defense, but as Yoshikawa Sensei and Gabi has already mentioned, but um, as of November 2022, more than 2,000 potentially hazardous asteroids has been discovered. So these potentially hazardous asteroids would impact to the Earth because of it would impact to the Earth, but it's not likely happen in a quite in a few years. And then so this is the NASA's the US Together surveys summary, but in the US Together survey for the planetary science and astrobiology, the recommend the first complete the DART mission in 2023. So it's has been finished. And then launch the NEO Surveyor in 2026. So the NEO Surveyor mission is a telescope mission that the Yoshikawa has mentioned. So it will be delayed to launch this NEO Surveyor, but it's coming in within a decade. And after that, the US Digital Survey recommend to conduct the rapid response Flyby mission by the end of 2032. Okay, so the one of the necessity of rapid response exploration is as the US Digital Survey has asserted, the rapid response mission is very important in the field of planetary defense. So in order to understand the characteristic of asteroid, before taking some kind of measure to mitigate the hazardous impact. So this rapid response flyby mission is it's not the mission to mitigate this hazardous asteroid, but it's the reconnaissance mission to understand the hazardous asteroid very well. There is another motivation of the rapid response mission. Maybe some of you already know, but on the October 19, 2017, the interstellar object flying from outside of solar system was discovered for the first time in the history of astronomical observation. And the researchers, we have never directly explored such a interstellar object before. So the researchers are paying attention to explore this interstellar object directly. Okay, so and then this interstellar object is in hyperbolic orbit with respect to the solar system. So it's coming to the vicinity of Sun and the Earth, and then just escape quickly to the solar system. That is why we need a rapid response exploration mission to explore in order to explore such interstellar object. So as a mission designer, I was thinking that the potential scenario to perform the rapid response exploration. So there is basically three options written here. The one of the option is direct launch from the Earth. The other is loitering in the space, particularly at Lagrange point. And the third option is loitering in the Earth resonant flyby orbit. So the direct launch option is launch spacecraft just after the target object is found. Okay. And the second option, the loitering at Lagrange points, is keep spacecraft in the halo orbit or Lagrange point orbit. And just after the discovery of the hazardous asteroid or interstellar object, the spacecraft escape and aim for the target object just after this discovery. And the third option is the loitering in Earth resonant flyby orbit. So Earth resonant flyby orbit is is orbit that periodically fly by to the Earth, where the spacecraft periodically fly by to the Earth. So the in this Earth resonant orbit, spacecraft can perform Earth gravity assist, for example, once a year. So the third option is keep spacecraft in this Earth resonant flyby orbit, and then just after the discovery of the hazardous asteroid or interstellar object, utilizing the Earth gravity assist, the spacecraft target to this object. So this is a kind of trade-off matrix of these three options. Okay, there is some kind of difficulty for each scenario. The difficulty of direct launch is obviously the rocket must be ready at any time. Okay, so which is difficult to do because the hazardous asteroid would found in the coming 10 years, or perhaps we have to we will not find such a hazardous asteroid in this 10 years. So anyway, we have to keep the spacecraft ready for 10 years or 100 years, and it may not happen or happens. So the difficulty of this loitering at Lagrange point is the equilibrium point of the Earth and the Sun, or Earth or Moon. Anyway, it's the energy with respect to the Earth is very small. So that is why the escape energy. So we have to gain more energy to fly by or access to the such a target body. So we need a large acceleration through electric propulsion or chemical propulsion, which needs the relatively larger system. And the third option, the loitering in the Earth resonant flyby orbit is because if we just use one spacecraft, we can only perform the Earth gravity assist once a year. So that is why we need to distribute, for example, 10 spacecraft that in this Earth resonant flyby orbit in order to perform the Earth gravity assist almost any time. Okay. So and then the concerning mission class, I'm thinking that for the option 1 and 3 is doable by micro or small spacecraft. But option the second option, Lagrange point option, we need a larger spacecraft. The problem of this difficult direct launch is we need a large launch vehicle. So although the spacecraft is small, we need a large launch vehicle to send the spacecraft to deep space. The third one, the loitering in the Earth flyby, is we could use a ride share, so we don't have to prepare the dedicated large launch vehicle, but we need about 10 microspacecraft. So the first option is is the one of the most difficult point of the first option is we need a launch vehicle capable of immediate launch. So and it's really difficult, for example, in like Japan. So maybe the US can do such kind of scenario, but it's difficult for Japan or probably most of the country. Second option is we need a relatively large mission, and then the ESA's Comet Interceptor is trying to do this approach to intercept the long period comets. And the third option is, I'm going to explain the detail in the next slide, but I'm going to propose a more cost-effective way to including multiple asteroid flyby while waiting. So it's the waiting time is not useless. It's very useful for the both planetary defense and planetary science. And then in this talk, I want to propose this third approach. Okay, so the Earth resonant flyby orbit is in the Earth resonant flyby orbit, spacecraft perform Earth gravity assist, for example, once a year or once in 2 years. Okay, because there is Earth gravity assist change the spacecraft trajectory drastically. We can fly by at least one asteroid between this Earth to Earth leg. Okay, so we call the asteroid flyby cycler orbit. And then Destiny Plus, which is I'm working on, and NASA's Lucy or NASA's Contour mission has employed this kind of asteroid flyby cycler mission. But anyway, we can in this asteroid flyby cycler mission, asteroid flyby cycler orbit, it's alternating asteroid flyby and Earth sync by, asteroid flyby and Earth sync by. And then the fuel consumption is very small, like 10 meter per sec per year, which is very doable by micro or nano spacecraft. And then we can fly by one near Earth asteroid per year. So this is the example trajectory, but as you can see, there is a 5 asteroid shown in this flyby cycler orbit. And then we can fly by such orbit with very, very small delta V. The JAXA Destiny mission is trying to implement this asteroid flyby cycler trajectory as the extended mission. So the nominal target of this Destiny Plus mission is this Phaeton. And after this Phaeton flyby, we are thinking to perform 2005 UD flyby, Hercules, Blancpain, and Tantalus flyby using this flyby cycle orbit. So that because the fuel consumption is very small, basically the spacecraft can fly by asteroid almost infinitely until the lifetime, until the spacecraft, during the spacecraft is surviving. I'm going to show you how many target body exist, or how many target body can be selected between this Earth to Earth leg. So this is an example of the Destiny's case, but I'm going to show some kind of table that Destiny can fly by in this third asteroid Earth leg. Here, this is a list of the potential target asteroid that Destiny can fly by. But there are more than 150 candidate asteroid that with relatively small delta V consumption for the Destiny. So it includes Hercules, Itokawa Ryugu. So we can revisit the Itokawa Ryugu if the scientist or there is some kind of interest for the scientist or the other people. So there is quite many targets can be selected using this flyby cycler orbit. So using this approach, the ISA structure is started to proposing a new small body exploration strategy. As of November 2020, as Ishikawa-sensei mentioned, more than 1 million small body has been discovered. So, and then the Hayabusa has 2 successfully conducted sample return mission, but the rendezvous type sample return mission understand the asteroid in detail. On the other hand, it takes a really long time to performing the rendezvous type sample return mission. But if you can do a multiple asteroid flyby mission like Disney Plus, which can be doable by relatively small spacecraft or perhaps micro spacecraft, we can extensively explore the more asteroids. Although the flyby is just a one chance, so it's not detailed exploration, but it's the multiple flyby can visit really a lot of targets. So yeah. So and then I want to connect to the rapid response mission from this multiple asteroid flyby mission story, but if you can create kind of deep space constellation on this asteroid flyby cycle orbit, for example, if you can, so as I mentioned, this kind of mission is doable by a micro or nano spacecraft. That is why we can easily launch like more spacecraft, like 10 spacecraft. If you can send, for example, 12 spacecraft in the deep space, and if you can create kind of a deep space constellation, then we can fly by the one asteroid per month. So which is the it's changed the everything drastically. It's drastically changed. So far we directly explore the asteroid. For example, once a few years or once a few years. But if you can create this kind of deep space constellation in this orbit, we can directly explore the asteroid every month. It's changed the world. And also, if this one spacecraft perform the orbit correction maneuver just before the Earth gravity assist, because Earth gravity assist can change the trajectory drastically, we can perform the rapid response flyby. Okay, so this is the kind of image of the rapid response flyby via deep space constellation. But we are creating such a deep space constellation. We launched about 10 spacecraft in deep space, and at least one spacecraft performing, for example, Earth's gravity assist in almost every time. This one spacecraft performing Earth's gravity assist to target to some kind of interesting body like interstellar object or hazardous asteroid. So so assembling such a spacecraft constellation in deep space enables Earth's gravity assist any time that helps to perform that rapid response flyby. So we have done a quick conceptual study of spacecraft system. And then considering the scientific requirement, we want to carry about 3 to 8 kilogram telescope or scientific instruments. So it will be feasible with 12 AU CubeSats, but probably I think it's better to make it larger, like 50 kilogram micro spacecraft. But that is, I think, enough. So we don't have to create like several hundred kilogram spacecraft, but the small micro spacecraft will be fine. Propulsion system capability is 10 meter per sec. Well, moderate to be is better, but 10 meter per sec is not enough. So that is why we can demonstrate like advanced electric propulsion or advanced propulsion system, and also even the solar cell works for this type of mission. The one of the difficulty of such a system is we want to send 10 spacecraft in deep space. The Earth distance is about 0.5 AU, so it's really far to communicate. So we need a deep space antenna, like deep space network or such kind of big antenna to communicate to this spacecraft. That is why we have to put a lot of autonomy on the spacecraft to operate, for example, 10 or 100 spacecraft. So the autonomous operation and particularly the autonomous orbit determination is critical technology to reduce the dependency on the ground station. So there is, I want to show the significance of this deep space constellation concept in the three different perspectives. The planetary defense perspective, because it's all small sat based, and then we need to send more than 10 spacecraft, and more is better. So it's all small sat based. So I'm thinking that international collaboration would be easily facilitated for such kind of mission. So if we can prepare, for example, large launch vehicle, and then many countries prepare the 50 kilogram micro spacecraft send at the same time, then we can create such a deep space constellation. So I think this is also really good to in the planetary defense perspective, but because it's planetary defense is not the problem of one specific country, but it's the problem of the world. So we can protect the Earth together in the world. So this is the one of the contribution to the planetary defense. Second part is space exploration and technologies. We need a continuous. We need to send a lot of spacecraft to the deep space. So we have a lot of chance to improve technology, and also we can develop technology. So it's really good chance to develop the industry and human resource through that kind of continuous tech demo opportunity. And third point is the planetary science. Obviously, if you can fly by multiple asteroid, for example, once a month, we can gain statistical information of small body that enhance the our understanding of solar system very well. And also, if we are lucky, we can also perform the world first direct exploration of interstellar objects, which nobody has been never seen directly explored. So it is third significant of planetary science. Okay, so in the conclusion, in order to realize multi-cluster flyby and rapid response flyby of small body, we propose the concept of deep space constellation using asteroid flyby cycler. And I show the significance of this concept from three viewpoints: planetary defense, planetary science, and space exploration technology. And the final remark is, why don't we work together to realize the world first interstellar object exploration and also protecting the Earth from the asteroid impact. Okay, so that's it.